In this problem, we're going to be looking at a little bit more complicated rigid Euler buckling problem. So in the problem statement, it's given that our spring stiffness coefficient is going to be 50 kips per foot, and that spring is going to be applied at point C. We're also going to have a hinge at point B where the system could potentially buckle, and you have a P applied to, or a force P applied to the system. And so we want to find what is the P critical of buckling for this problem. And so to start off, one of the main things to do is write our main equations for the problem. So main equations. And so for this problem, the most important one is our Hooke's law equation, which is going to be our force in the spring is equal to our stiffness coefficient times our d, or our distance that the spring deforms. Another good thing to note is that our sum of the moments is going to be equal to 0, which meaning it's going to be a static problem. Another good thing to assume, rather not really a good equation, but a good assumption for Euler buckling problems, is that our sine of theta, and the theta being the deflection at point A, is going to be approximately equal to theta, which will make finding the distances that point C and the spring deform easier to find. First thing we're going to want to do is we're going to draw our free body diagram. So step 1 is going to be our free body diagram. And so I've already drawn it up here for you guys. So this is what our free body diagram is going to look like. The deformation of the system is greatly exaggerated just so we can see the distances easier. So we have our force P applied at the top, which stays in line with our reactions at the bottom. And then at point C, we have our biggest deflection of 10 theta, because that's a distance of 10 feet from the bottom. And then we also have our spring having a deflection of 5 theta. Now the reason that at point C the spring deflection is 5 theta is because it is at the center of that first section between B and D, and so it's going to be exactly half of the deflection at point B. Now that we have our free body diagram, we can find what the force in our spring is going to be. So the force in our spring is going to be equal to the K times D, which is going to be equal to K, and that distance that is the spring deflects is going to be a 5 theta. So that means our force in our spring is going to be 5K theta. Now, in order to find P, we actually have to do an extra step. We can't just take the sum of moments about point A right now. Since it's in line with the reaction, we wouldn't be able to solve for P. So our next step that we're going to have to do is we need to find F3 in terms of P. So in order to do that, we need to make a section cut of our system. So what we're going to do is at step 2, find F3. And so we're going to draw another free body diagram cutting the system at the hinge. So now if we redraw our system, right at the hinge, we have a force of P pushing down on it. We have our F3, and then there's also the force of our spring. And lastly, there's going to be 2 forces at where we unconnected the hinge from the rest of the system, which in this case we're going to call them F12 and F11. And lastly, our distance from the original guide, this distance right here, is going to be 10 theta. So now that we have this second free body diagram, we can take a sum of the moments where F11 and F22 meet, which is at the hinge. So we take a sum of moments, assuming that clockwise is the positive direction. We get sum moments is equal to 0, and that's going to be 0 is equal to a negative P times 10 theta minus F3 times 6 feet, and then minus the force of the spring times 3 feet. And so now we want to rearrange this so that we have F3 in terms of force P. So now we get that F3 is going to be equal to a negative P times 10 theta plus, and then I'm going to substitute in what we got for the force in the spring, which is this K times 5 theta. And so we get 15 K theta, and all of that is going to be over 6. And so now that we have this, we can go back to our original free body diagram and take a sum of moments about your point A, and then you can solve for what you get for P. So now let's get some more space, and so now we'll do step 3, which is going to be taking another free body diagram, step 3. So now we got the sum of moments about point A, which we're still going to assume that clockwise is the positive direction, just to keep track of our positives and negatives. And so now we get that 0 is going to be equal to a negative F3 times 16, minus force in our spring times 13. And these distances are coming from this original free body diagram that we figured out in step 1, where we have those distances on the left. So our force of our spring is 13 feet from point A, and our force F3 is 16 feet from point A. So that's where those distances come from, so 16 feet and 13 feet. And so now we're going to plug in what we know for F3 and our force in the spring. So we have 0 is going to be equal to a negative P times 10 theta plus 15 K theta over 6, that times 16 feet, minus 5 K theta times 13. So now we're just going to simplify this equation a little bit. So we get that 0 is going to be equal to P 160 theta, because we're bringing that 16 over, and that is going to be over 6 minus 240 K theta over 6 minus 65 K theta. And now before we plug in the values for K that we know, we can actually get rid of some terms. So since each term has a theta, we can get rid of that. And that's about it. Everything else we are going to have to plug in and solve for, since we can't get rid of any K's since that first term does not have a K. And so now if we plug in the values that we get, so we get 0 is going to be equal to P 160 over 6 minus 240 50 times 50 kips per feet over 6 times 65 times 50 kips per foot. And so now that if we take our P to the other side and solve algebraically, we should get a P that is equal to 46.9 kips. And that is going to be our critical buckling force.